In this lecture, we are going to start with harmonic functions. So what are harmonic functions that we have to study today? And we are going to see some important points regards to harmonic functions. See, uh, before I start with harmonic function, one small note that I forgot to mention in continuity and differentiability. So with regards to continuity and differentiability of a complex valued function, I have an important note that probably I have forgot to mention, so that I'm mentioning it here itself. Okay, so now see, what I mentioned in one of the lectures was that if f is defined from D to C and D is a subset of D is a domain. Okay, domain means what? By domain, I mean connected and open set, and it is a subset of C. Now, if I'm saying that fz is equal to u plus iota v, then I can write that f is um, continuous. F is continuous if and only if u and v are continuous. So what I want to say is that if u and v are continuous, then f becomes continuous, let's say at a point z naught. Okay, so if my u and v are continuous at a point z naught, then my f obviously becomes a continuous function. This is something that we know. But is it true for differentiability also? Is it true for differentiability also? Okay, obviously continuous means what? The limit should come and limit should be unique. Okay, so should be path independent. So if u and v are having a path independent limit and their limit exists, so then fz becomes a continuous function. Okay, so if and only if, that means what? If fz is continuous, then u and v are continuous, and if u and v are continuous, then fz must be continuous. Now I'm saying, is it true for differentiability also? That if my u and v are differentiable, that is, if u and v are differentiable at a point, let us say z naught, then fz is differentiable at that point. Is it so? That I wanted to really address, and that's why I have kept this note. Okay, so just take an example. I'm just giving you an example. Just take u is equals to x and v is equal to y. Not y, I think minus y. Just take minus y. So I've taken u is equals to x and v is equal to y. Clearly, clearly this particular function u is equal to x. So x and minus y, if I consider them as a two variable function, so I know that these are linear functions in two variables. So basically it is x here and bxy simply minus y. So clearly both u and v are differentiable. Let's say, let us take one point and then I'll differentiable at 0. That's not a problem. Okay, they are differentiable at 0, but fz is equals to x minus iota y, which is simply z bar, is not differentiable. Okay, it is not differentiable at origin. I hope we have done this particular thing, because if it is differentiable, then I told you this thing very earlier also. Limit z tends, sorry, h tends to 0, f of 0 plus h minus f of 0 upon h. It implies what? It implies h bar minus 0 divided by h. And let us say that h is nothing but del e ki power iota theta, and h bar would be equals to what? Del bar e raised to power minus iota theta. And we know that what is del bar? Del bar is simply del only, because if I'm talking of del, del is a real number. So del bar is the same. So it will be like del e raised to power minus iota theta, and divided by um, del raised to power iota theta. So in any case, it depends upon, what should I say? It depends upon path. Or otherwise, if you want to write, you can write h as simply h1 plus iota h2, and then I can write h2 is equal to mh1. So from that also we can prove that this limit turns out to be 1 minus iota m divided by 1 plus iota m. So clearly part dependent limit. So therefore function is not differentiable at 0. However, both u and v are differentiable at 0. So in continuity, this statement works that if u and v are continuous, then f will remain continuous at that point. But in differentiability, it doesn't work. So this is one of the important things that I forgot to mention in the previous lecture. So therefore, I have mentioned it here itself. Now let us move to our today's topic, which is harmonic functions. Now let us first write what are harmonic functions. See, a real valued function, a real valued function phi is called is called harmonic function if it satisfies if it satisfies Laplace's equation. Okay, it satisfies the Laplace's equation, and I'm going to write what is Laplace's equation later on. Okay, if it satisfies Laplace's equation, and in order to satisfy the Laplace's equation, what is the necessity? If it has continuous uh, partial derivatives, partial derivatives of second order, um, and and satisfies and satisfies uh, satisfies Laplace's equation and satisfies Laplace's equation in some domain uh, omega. So I'm saying that if a real valued function is such which has continuous second order partial derivatives and it satisfies the Laplace's equation. So what is Laplace's equation? That is phi xs plus phi yy equal to 0. So if it has second order partial derivatives which are continuous, and also if the function phi satisfies this partial differential equation, which is phi xx plus phi yy equal to 0, then we say that the function phi x is a harmonic function in omega. So then we say that phi is a harmonic function in the domain omega. Other way of writing this is del square phi is equal to 0. This operator del square is referred to as the Laplacian operator. This operator is also called as the Laplacian operator. Okay. Lately, we are going to see an important note with regards to analytic function, but just for the sake of defining things, I'm defining it right now. We're going to see it, don't worry. But just definition I'm writing. A function v is called a harmonic conjugate of a harmonic conjugate of. I'm not writing conjugate, okay? A harmonic conjugate of u in omega if f is equals to u plus iota v is analytic in omega. So if my function f is analytic in omega, then this particular v is called as conjugate of u. not this conjugate. Okay, don't get confused with z bar. I'm not talking of this. That is, I'm not talking that v is equal to u bar. It is just said a harmonic conjugate. I mean, this is just a terminology, and you have to remember it, that v is called as harmonic conjugate of u if on a domain omega, if my function is analytic on that domain. And we'll come to this, don't worry. Okay, but just now remember this particular term. Another thing we have to see, that this particular harmonic conjugate is always unique. That is, if I'm writing here v, that is harmonic conjugate of u, harmonic conjugate of u is unique up to a constant, up to a addition of a constant. Okay, so what I want to say is that if v is a harmonic conjugate of u, then some other conjugate harmonic conjugates can be there of the type v plus c. This is what I want to say, that if v is a conjugate of u, then other harmonic conjugate can only differ by by a constant. Okay, so other harmonic conjugate can be v plus c. So in that sense, v is a unique harmonic conjugate up to a addition of a constant. Let us see how. So I'm just writing it here, that if I'm just giving you a statement, v is harmonic conjugate of u, harmonic conjugate of u if there exist any other harmonic conjugate, if there exists any other harmonic conjugate, it it is nothing but v plus some constant. Okay, this is what I want to convey. Okay, so see how. I don't know why these pens are keep on changing. Okay, so proof. How to go about it? See, I already know that my uh, what you can say, v is harmonic conjugate. Let us take v1 to be harmonic conjugate, v1 be harmonic conjugate of u. Let us take our function v1 to be harmonic conjugate of u. Now, if my v1 is a harmonic conjugate, then it implies what? It implies that f is equal to u plus iota v1 is analytic on some domain, let's say omega. And I have already stated that if f is equal to u plus iota v is, if v is harmonic conjugate of u, if v is harmonic conjugate of u, then f is equal to u plus iota v is analytic. So I already know that f is equal to u plus iota v is analytic. I have just taken another harmonic conjugate, that is v1. If v1 is harmonic conjugate of u, it implies that f is equal to u plus iota v1 is analytic on omega. It implies that f minus small f is also analytic on omega, which is nothing but iota v1 minus v is also analytic on omega. And if you remember, we have done this thing in previous class, that if f is, I'm just writing it here for your memory, if f is analytic plus either real valued or imaginary, purely imaginary, then f must be a constant. If you remember, we have done it in the previous class. F must be a constant. It implies what? It implies that capital F minus f, which is analytic and also purely imaginary, it must be a constant. And what does it imply? It implies iota v1 minus v should be a constant, and it implies that v1 should be equals to v plus some constant. So if any other harmonic conjugate we are talking, it can be not, it has to be the originally that is the harmonic conjugate plus C. So what I want to say that if V is a harmonic conjugate of U, and if there exists some other harmonic conjugate, it can only differ by a constant from V. There is no other way out. Okay, so this is one thing that you should remember. Now, a few other things, points that really need to take care of is like one of those is this. So I'm giving you some notes. Note number 1. The first note is that whenever we are, if I'm saying that F is, so I'm just saying we cannot choose U and V arbitrarily. We cannot choose U and V in arbitrary fashion. Okay, that is, we cannot choose U and V arbitrary such that F becomes analytic. That is, it may be possible that your U and V are harmonic. Okay, we cannot choose. I should write harmonic functions. Harmonic functions U and V arbitrarily such that F becomes analytic. And I'll let you know how to find conjugate and all those things later on. There are methods. But initially, just I want to claim that we cannot choose any two arbitrary functions, any two arbitrary harmonic functions such that F becomes analytic. Okay. So let's say what I want to convey is, and let's say I take U is equal to simply X. And let's say V is equal to simply minus Y. Both of them are harmonic functions. See, if I take del square U is equal to what? 0. And what would be del square V? Del square V would be 0, clearly. So I know that both U and V are satisfying the Laplace's equation, and both of them possess a second order partial derivative. So both are satisfying the Laplace's equation. Satisfying the Laplace's equation. And also the second order partial derivative exists for both. It implies both are harmonic function. But is F analytic? Clearly not. Is F analytic? We have proven already that if Fz is equal to x minus iota y, it is equals to what? Z bar, and it is analytic nowhere. Okay, it is analytic nowhere. So you have to keep a care of how to choose functions so that it becomes analytic. Okay, so if I choose how to choose harmonic functions U and V such that Fz becomes analytic. Okay, so we have to take care of that. Another thing is that uh, uh, that if we want to say that a function is harmonic, then Laplace's equation must be satisfied on some domain. Laplace's equation must be satisfied on some domain. And lately I'll write it as simply connected domain. I'll tell you what is simply connected domain. Just write a term right now saying must be satisfied on a domain, or rather I would say a simply connected domain. And what is simply connected domain? I'll let you know, don't worry. So I want to say that it cannot be the case that if my Laplace's equation is valid for certain points and which is not a domain, that is which doesn't form a connected and open set, I cannot write that. And more appropriately, I would write simply connected domain, and I'll let you know what is a simply connected domain. Okay, but just for the sake of giving you an example here, so that you will be able to understand. Matlab, what I want to say is that if I take, let's say, U, which is x cube minus y cube. Now, if you say what is del square U, so del square U is what? It is 3x square. And again derivative, so it will be 6x and again minus 6y. So it is equal to 0 if and only if x equal to y. Okay, so it satisfies Laplace's equation. It satisfies Laplace's equation on some set S, which is x and y, such that x equal to y. But clearly you know that x equal to y doesn't form a connected set. Okay, it doesn't form an open set. Sorry, it doesn't form an open set, because if I'm taking any point, then its neighborhood is not contained in that line. So clearly it doesn't form a domain. So I will not say that my u is a Laplace a harmonic function. So u cannot be claimed as harmonic function. Cannot be claimed as harmonic function. This is an important thing. Now, another important thing that arises from here is called as the complex Laplacian. I'm giving you a relationship between complex Laplacian and the original Laplacian that you study. So, relationship between complex Laplacian, which is denoted by this, and Laplacian. So, another important thing, it may be useful later on. So, that's why I'm just giving you this particular thing. So, let us construct a complex Laplacian. Construction of complex Laplacian. So let us consider u as a function of x and y, and rather I would write u um, x. I can write z plus z bar upon 2, and I'll write z minus z bar upon 2 iota. And it is a practice in complex analysis to treat both z and z bar as independent. So I'll treat both z and z bar as independent, and I'm going to just find a derivative, which is del u by del z at first. So what would be del u by del z? It would be um, simply del u upon del x into del x upon del z plus del u upon del y and then del y upon del z. What is del u upon del x? So del u upon del x is fine. It is simply ux I'm going to write. And what is del x upon del z? Del x upon del z is simply 1 upon 2. So I'll simply write 1 upon 2. Here I'm just writing ux. And what is del u upon del y, which is uy, and what is del y upon del z? So if I say del y upon del z, it is simply equals to 1 upon 2 iota. So it is minus iota upon 2. So minus iota ui. I hope it is clear. Now if I take another derivative of it, which is differentiating with respect to z bar. So if I take this, what I'm going to write this particular thing as, so I'm going to write it as del u upon del z bar, which is equals to what? Which is equal to writing del upon del z of this 1 over 2 ux minus iota ui. Okay, now I'm writing it here. So what it will be equals to? So it is equivalent to writing. So I'm just writing it here. So sorry about it. In del square. Okay. It is del square u upon del z bar. It is equals to what? Differentiate with respect to ux. I'm going to differentiate with respect to ux. Uh, so what I'll get? 1 upon 2 is outside. So I'm just keeping 1 upon 2 outside. So it will be del upon del x. Del upon del x. And then I'm writing ux minus iota y and del x upon del z bar, and then plus del upon del y ux minus iota uy and del y upon del z bar. Okay, so after all, I'm going to get this del square u upon del z bar, which is 1 over 2. What is del? This will be, I think, uxx minus iota uyx. And what is del x upon del z bar? So del x upon del z bar is what? It is simply 1 over 2. So I'll simply write 1 over 2 here plus uxy minus iota uyy. And what is this fellow? Del y upon del z bar. So del y upon del z bar would be minus 1 upon 2 iota and simply minus iota upon 2, I'll write. So it is 1 over 4 uxx plus uyy plus iota, and in bracket you are going to get what? You're going to get uxy minus uyx. Okay, so this is nothing but del square u upon del z bar. Okay, now if u has continuous second order mixed partial derivatives, then what happens? This both of them are equal. This is from multivariate calculus. This is the result that if u has a continuous second order mixed partial derivatives, then uxy is equal to uyx. So this becomes 0. And if u is a harmonic function, if u is a harmonic function, then what happens? This also becomes a harmonic function. That is del square u upon, this becomes equals to what? 0. If u is a harmonic function, then del square u upon del z bar becomes 0. So this particular notation I'm going to give, this is referred to as a complex Laplacian. This particular thing is referred to as the complex Laplacian. What is del square u? Del square u would be equal to 0, provided u is harmonic. If u is harmonic, then uxx plus uyy would be 0. And if that is the case, then del square c u equal to 0. And this del square c is called as the complex Laplacian. So what is a complex Laplacian? Nothing but this. That is, I can write it as del square del z bar. So this is what is referred to as the complex Laplacian. Now, if I compare, let's say if I had not this, if I just wanted to compare, not write it as a harmonic function and put it as 0, then what was happening was that if the first order partial derivatives are continuous and second order partial derivatives are also continuous, second order partial derivatives are continuous, then what happens? Then happens what? Uxy becomes equals to what? Uyx. Okay. Then I can write that my del square c u is equal to simply del square u. If u becomes harmonic, then it becomes 0. But otherwise, I can write that my del square c is equal to what? Del square c u is equal to del square u. Here I can get a wonderful result. I think I have made a mistake somewhere. So I think this was, I think, somewhere. I have to write it. I think 4 was common. Okay. It is equals to 1 upon 4. So sorry about it. Okay. So then it is equals to, that if I'm not stating that u is harmonic, then what will happen? Del square u is equal to 1 upon 4 del square cu is equal to 1 upon 4 del square u. Here I can establish a relationship between del square c and simply del square, which is this. And it implies what? If I want to write my del square in terms of complex Laplacian, it is going to be equals to 4 times del square del by del z and del by del z bar. So this is how it is going to be. So if I want to write my Laplacian in form of complex Laplacian, so this is what is complex Laplacian, then this is the result. You should remember this. It may be asked in your examination also. Now let us draw our attention to the harmonic function and analyticity. So what is happening is, see, now this is an important thing that I'm going to write. Now, if f is equal to u plus iota v, f is equal to u plus iota v, if it is analytic on an open set omega, then what would be the CR conditions? We know that CR conditions would be, then CR conditions hold, right? If function is analytic, then CR conditions hold, that is ux is equals to vy and uy is equal to minus vx. Right? Now, one statement I'm giving, if second order partial derivatives exist and are continuous, then what can we write? Then I know that I can differentiate this partially with respect to x. So I'll get simply v by x. Okay, I'm differentiating. Yes. So partially differentiating with respect to x now. So this is, and partially differentiating with respect to y, I'll get simply minus v by x. Okay, if I add the two, then what does it what happens is uxx plus uyy becomes equal to 0. If the continuous, if the second order partial derivatives are continuous, then always remember that the order of derivative is immaterial. Order of the derivative is immaterial, and vxy becomes equals to v by x. So for that matter, your right hand side would become 0, and is harmonic on, u becomes harmonic on this open set omega. However, this particular thing, it's not necessary to write, because lately we are going to understand that if f is analytic on an open set omega, if f is analytic on open set omega, then all the higher order partial, if fz is analytic, if fz is analytic on omega, we're going to see later on that all the higher order derivatives are also analytic, which implies that all the higher order partial derivatives of u and v exist. All the higher partial derivatives, higher order partial derivatives of u and v exist. Okay, so what I want to say is that if fz is analytic on omega, lately, I mean, in the later sections, we are going to see that f dash z, f double dash z all exist. So if they all exist, it implies that all the higher order partial derivatives exist, and in fact, they are continuous also. So this doesn't need to be there, but right now I have placed it so that you become aware of it. Okay. So uxx becomes equals to vxy, and uyy becomes equals to minus of vyx. And if the second order partial derivatives are continuous and they exist, then vxy becomes equal to vyx. That is, the order of derivative is immaterial, and this goes 0. And it implies that uxx plus uyy equal to 0. It implies u is harmonic on omega. Similarly, we will see that if f is analytic, then if f is analytic on omega, then v also satisfies the Laplace's equation. V also satisfies the Laplace's equation, and it implies that V is harmonic on omega. Okay. And remember, I have already stated that if U and V are harmonic, on omega, it does not necessarily imply that F is analytic. That is something that you know already. Okay, it does not necessarily imply, you have to choose it in a certain way. Okay, so for example, I've given that example already, that I know that my u is harmonic, that is u is equal to x, and I know that v is harmonic, v is equal to minus u, but I know that fz is equal to u, sorry, x minus iota y, which is simply z bar, is analytic nowhere. So you have to take care. Okay, analytic nowhere. So we cannot arbitrarily choose u and v harmonic function such that fz becomes analytic. But if fz is analytic, u and v are harmonic for sure. That is true anyway. Okay. So this brings us to a sort of theorem. I can write it here. I'm writing it here. Okay, so I'm writing it here. That let omega be an open set, omega be a open subset, rather, open subset in C, then the real and imaginary parts, imaginary parts of an analytic function, of an analytic function in omega are harmonic in omega. Okay, are harmonic in omega. So if I'm talking of analytic function, then both u and v, that is the real part and imaginary part, are harmonic in omega. I hope this is clear to you. So these are some very important things. Now let us move to another important thing that I'm going to write, and it's an important thing that it needs a mention here. Okay. One other important thing before I head to uh, the completion of this lecture is that if fz is equal to u plus iota v and is analytic on open uh, subset or open set omega, then we know that fz square is also analytic. Then fz square is also analytic on omega. So what does it mean? It implies that fz square is what? It is equals to u square minus v square plus 2 iota uv. It implies what? It implies that u square minus v square and uv are also harmonic on omega. Are also harmonic on omega. So this one should take care of. And if there are two functions which are u and v which are harmonic, I think this you can prove on your own. So I'm not going to prove it. I'm just going to write it that if u and v are harmonic, if u and v are harmonic function, then their linear combination is also harmonic. Then their linear combination is also harmonic. That is alpha u plus beta v is also a harmonic function. Is also a harmonic function. Okay, now let us move to another important assertion, and that happens to be the last assertion of the day. That if u and v are harmonic conjugates of each other, okay. So what does that mean? I'll come to that. Harmonic conjugates of each other in some domain, then u and v must be constants. See what I want to say. I already told you that if v is a harmonic conjugate of u, if you remember, I had already told you that if v is a harmonic conjugate of u, okay, if function v is a harmonic conjugate of u, when it is said a harmonic conjugate of u, when f is equal to u plus iota v is analytic. This is something that we already know, that v, a function v is said to be the, what you can say, harmonic conjugate of u whenever f is equal to u plus iota v is analytic. This is something that we already know. Now, according to this, we know that if u and v are harmonic conjugates of each other, it implies what? It implies that f is equal to u plus iota v is analytic. If v is harmonic conjugate of u, if v is harmonic conjugate of u, it implies that f is equal to u plus iota v is analytic. And if u is harmonic conjugate of v, then it implies that v plus iota u is also analytic. So let us denote it by some other function name, that is g. If u is harmonic conjugate of v, then v plus iota v, sorry, if u is harmonic conjugate of v, if u is harmonic conjugate of v, then v plus iota u is analytic. So I've given it as aim g. So let's say on analytic on some domain omega, analytic on some domain omega. Now, further, I can write that f, if I just take minus iota g, so what will happen? F is equal to what? U plus iota v minus iota g if I take, so it will be iota v minus u. So I'm going to get 2u. So 2u is what? F minus iota g. And simply if I do F plus iota g, what it is equal to? If I do F plus iota g, it is simply equals to 2 iota v, right? Now we have already know that F and G are analytic. So their linear combination is also analytic. Okay. Is that fine? Okay. And it implies what? U is analytic plus it is real valued. Okay. And this 2 iota v is analytic and it is real valued. Sorry, it is purely imaginary. It implies that both u, it implies that u is a constant and it implies what? It implies v is a constant. This is something that we have done in the previous class, that if a function u is if a function fz is analytic and purely real, then f is constant, and if fz is analytic and purely imaginary, then f is constant. Similarly, 2 iota v is analytic and it is purely imaginary. So it implies what? It implies that 2 iota v is constant. It implies v is a constant. So if both u and v are constant, it implies what? It implies that f dash z must be equal to what? 0 for all z belongs to D. I hope it is clear or not clear. Okay. And u and v are constants. So if I mean, if u and v are constant, then f dash it becomes equal to 0 for all z belongs to D. And this is what we had to prove, that if u and v are harmonic conjugate of, not D, sorry, on omega, if we, this is what we had to prove, that if both u and v are harmonic conjugate of each other, then u and v must be constant. This is what we have proven. And further, f dash z should be equal to what? It should be equal to 0. Because if u and v are both constant, then f dash z must be 0. In fact, g dash z is also 0. Okay, both are 0. I hope it is clear. Okay, so it implies what? It implies that if from here also you can say that f is a constant, and from here we can say that g is a constant. So I hope this sums up your problem, that if u and v are harmonic conjugates of each other on some domain, then u and v must be constants. So I hope in today's lecture you might have got a gist of harmonic functions. In next lecture, we are going to see some theorems regarding the construction of conjugates. That is, if v is given, can we really find u? Okay. So how to find all these things we are going to see. How to find harmonic conjugate we are going to see in the next lecture. Till then, take care. And please let me know if there is something that you are not following. Till then, take care. Bye-bye.